you're going to want to use this equation sheet just so that you start getting used to the geography, the layout of it. If you want to take notes or write on this as you're going for the next few days, that's fine. You have to have one that's not marked up for the exam, and I have lots of extra copies. So it's okay to write on it, but you can't use the written one, or if you don't write on it, it's fine, you can use it. Tommy?
Use the written one tomorrow.
Nice, though. Nice try.
Mine's printed on and I didn't do it.
Yours have stuff on the back?
Yeah.
Yeah, that was my master, so no worries. You got the special one. That's the super lucky one.
Yeah, guys, you're like 200 and 400 with a 30-degree angle, yeah.
All right. We're going to review all of the free response questions you'll see on the marking period exam tomorrow, and that'll also be a review for half of the semester exam as well. Got it? So, we studied centripetal force this marking period. This is not necessarily in order. I think we started with collisions, colliding. Yeah. Yes, exactly. All right. So centripetal force, we basically had three types of different centripetal force problems. Flying pig. Remember the flying pig? And she made like a cone shape as she flew on the string, and then we created a triangle with the weight of the pig and the centripetal force. You won't see one of those. Then I took a ball and I spun it in a vertical circle, right? You won't see one of those. On the marking period, not necessarily for the semester, but I'm just talking about let's get through tomorrow, okay? And then the other type of centripetal force was like a bug on a record or a car making a turn. Yeah, that's what you're going to see tomorrow. Okay?
So you said the spinning it vertically and the bug one, both of those, or not the spinning?
Not the spinning vertically. Just, we'll do bug on a record as an example, okay?
Wait, we're not doing phase?
No. Yeah, less talk, more listen.
It's really hard to come back.
I know, you missed each other. And robotics is gearing up, right? Yeah. Are you behind already because of the snow days?
Not really. We had we had a giant group chat on Facebook, and then we went to Martin because we thought the school was going to be closed down on Wednesday, but then the school wasn't closed down, so we had 2 meetings yesterday.
Okay. So this is a bug sitting on the edge of a record, and the record is spinning at 33 RPMs. Remember this? Yep, this is review. Revolutions per minute. And I want to know how big the record is if his feet are just sticky enough to hold himself there. So this is just like a car taking like a turn on an on-ramp or something like that. It's the same idea. So the centripetal force in this particular example is due to what? Friction, right. So I want you to look at your equation sheet and see if you can find centripetal force and friction. Where is it on the equation sheet? Yeah, I'm going to give you mu. Right in the middle, right here, right? These two? Okay. So yes, friction equals centripetal force in this case, also for a car going around a corner. So I need to give you some more stuff besides the speed of the record. I'm also going to tell you what mu is. And the mass of the bug could be anything, which means what? Mass cancels, you don't need it, exactly. So what I'd like you to do is try to flesh out these two equations right now. So kind of get used to the layout of the equation sheet and see if you can at least put down the variables. That's what you're solving for.
Are we trying to solve for the radius or the diameter?
The radius. Yep. Let's see how you did. Friction is mu times the normal force. What's the normal force in this picture?
Gravity.
Mass times gravity, just the weight of the bug, right? Centripetal force is either mv squared over r or m omega squared times r. Which of these two centripetal force equations would be the easier one to use in this particular example? Yeah, the one with omega in it, because it's going to be easier to convert RPMs into standard metric units for angular. What are standard metric units for angular speed? Radians over seconds. Good. So it'll be easier to go from revolutions per minute to radians per second than it would revolutions per minute to like meters per second, right? So I'm going to use this one in the example. I mean, you could use the regular old linear version, but it's just a little bit harder conversion problem. Yeah. You'll want to be in degrees even though we're using radians, because the purpose for that is when we do trig, and the angles are always going to be in degrees. Okay, it's a good question. W is angular speed in radians per second.
Okay. So when you see that revolution?
It is in revolutions right now, convert to radians. And since mass is anything, we can make mass go bye-bye, right? And we're solving for r, so this will end up, if I kind of boil it down now, mu g over omega squared. Does everybody see how I sort of skipped a couple of steps there to get r? Everybody got that?
So 33 of 80%.
No, we got to, it's close, it's almost there, but we got to do a conversion. So let's do that. So 33 revolutions per minute, and we need to get it to standard metric angular speed units. So revolutions goes to what? Radians. And minutes should convert to seconds. I'll let you get caught up. So it's 3.46 when you multiply and divide everything. Now you're in standard metric units for angular speed. What are the units for mu? There are no units, right? That's radians per second, so what should gravity be?
9.8.
Yeah, 9.8 is fine. That's a standard metric unit. So remember, radians is not really anything, so that'll all match, okay? So mu is 0.39. Gravity is 9.8 meters per second squared. And omega is 3.46 radians per second. And square out the whole thing, and you get R. And believe it or not, all the bunch of stuff cancels and you end up with just meters when you do all this. Because the second squared will cancel like here because of the squared, and you just have meters left over because radians isn't really a unit, it's like a ratio of arc length to Anyways, it works when you do this, okay? Convert to radians, yeah. It's a big record. I gotta admit, it's a big record. The radius is like this, so it's like one of those old laser disc things. Do you remember those?
Yeah, they're great.
They were awesome. They were like going to be the wave of the future.
What is CD?
Because it was like a CD, but it was huge. And they came out about the same time as CDs just started to hit the market, and they were a way to put like pictures, and they had a special player. They were pretty much, and it was like 1,000 pictures could fit on here. I don't know, it might have been more than that, but it was ridiculous compared to like what we fit onto our, cheapest phones right now, right? So, yeah, it didn't really catch on. So it's one of those. Question? Can you do this tomorrow?
Yes.
Okay. Excellent. All right, let's do another one. Torque, balanced torque. So, torque problems are teeter-totter problems. Remember me and Larry Weymouth?
Yes.
All righty. So, torque, teeter-totter problems. We did a homework problem that was a meter stick, and it had vegetables hanging from it.
Right.
Yeah? See, if you do your homework, then you can at least be like, oh yeah, there were a large lemon and a cucumber, I think.
Yes.
So,
You took a solid shot.
all right. So this is a meter stick, 0 and 100. And we're going to hang it from the ceiling, okay, at the 75 centimeter mark. And the center of gravity of the meter stick is at 50. We talked about center of gravity right before break. So it's as if all of the weight of the meter stick is concentrated at that spot. So I'll put C-O-G right here. You know what that means, right?
Yeah, fine.
Center of gravity right in the middle. And let's say the meter stick has a mass of 0.5 kilograms. So a half a kilogram. So if that was all, if it was just a meter stick hanging from a string, what would it do?
It would swing that way.
Yeah, it would swing which way, clockwise or counterclockwise?
Where does the clock go?
Yes. I have to do the same thing. I have to look at the clock to remind myself and then go, okay, that's counterclockwise, right? Yeah, if you're not sure, it'll spin, because then the rope, like the string will be the pivot point. If you're not sure, put your pen there and then go like this. Whee, and then you can tell, all right.
Wow. Is that always in reference to the right side then?
No, it depends on where the pivot point is. So you have to look at the individual picture and make that.
Whatever side people like, because I thought it was like balance, never mind.
All right,
Whatever.
I'll accept that. So this is going to cause counterclockwise torque. Remember, fancy T was torque. We're also going to hang a 1/4 kilogram mass on the end. Okay, right there. And that's going to be at the 10 centimeter mark, okay? It's going to be in a minute. So, which way will this mass cause it to rotate?
Clockwise. Oh, no, it's
Count-
gonna help the count.
It's going to help the counterclockwise torque, right? So Costa asks, is this thing going to be in equilibrium eventually? And the answer is yes. So since these both produce counterclockwise torque, we have to balance them against what? Yeah, and where would I put the mass to balance it? Yeah, way out here, close to the 100 centimeter mark. Go ahead, Varun.
So how can you tell if it's better, which way it will rotate?
It's different for every picture. So it depends on where the pivot point is in relationship to the applied forces. So that's what, I mean, I wasn't kidding when I said, like, sometimes I'll put, like, my pencil where the lever arm is and, like, pin down the pivot point and then go, oh, this will make it go that way. This makes it go that way. See what I mean? No, the pivot point is actually the string that's attached to the ceiling in this case. Okay. So now those two are going to balance against torque CL. Got it? That's the basic equation. Counterclockwise torque will equal the clockwise torque if it's in rotational equilibrium, if it's not rotating, if it's nice and balanced. If Larry plays fair, this will happen. Never did. This never did, but it could have if he had any sense of right and wrong.
Okay.
Clearly he just did. I'm over it, though. I like to think he's in jail. All right.
Maximum security prison.
That was probably white-collar crime. All right. Or Spider-Man underwear crime. All right. Counterclockwise torque is, or any torque, is force times lever arm. So what are the forces in this picture? The weight. And the lever arm?
Oh, it's the distance from the center of gravity? No.
From the string.
Right, from the string to wherever the applied forces are attached. So force times lever arm. So force here is just going to be mass times gravity. That's the applied force. And what's the distance of the lever arm? By the way, where is the torque equation on this sheet? Where's the torque equation? Find it. It is on the bottom, right here. Force times lever arm. Yes, you can. Absolutely.
Oh, you don't have to have gravity?
Don't have to have gravity. You'll see why. I'm going to write it in, but then you'll see why it's not. It's going to cancel. Yeah, so, right, the 75 centimeter spot is the pivot point. That's the point around which the torques are balanced. So what's the lever arm from here to here?
65 centimeters?
65, yes. Go ahead.
So when it just, in these type of equations, isn't it just the force times the distance?
Yes.
When we're doing 0.65, I can bring in meters.
Yep. Yeah, it's actually, because this is a conservation rule, stuff equals stuff, right? This stuff equals this stuff. As long as the stuff is the same, it doesn't matter what units you have. So if you want to stay in centimeters, that's okay, but make sure it's centimeters all the way through. If you want to drop out the 9.8, you could do that, because you're going to have 9.8 here, and here, and here. It'll be in each algebraic expression, therefore it will, right. But it won't hurt to leave it in.
What if you didn't give us the 75?
Like if you were solving for that spot, then you'd have to know where everything else is. Like here I gave you an unknown mass, so you'd have to know everything but that, and that would be a pain in the patoot, because every single expression would have an x value, correct?
Oh, yeah.
So you're saying you wouldn't do it?
It's possible, but not very likely for tomorrow, just for the sake of time. All right, do the same thing with this. Let's see if you get it right. You, go. Bam, now. Do it. Yes.
Does the last mass have a specific spot? Like, do we know the level?
Oh, yeah, it does. Sorry. I had otherwise too many unknowns. Let's put it at the 95 centimeter mark. Thank you. Yeah. Yep. Can I write this one in, this expression? Are you ready?
Yep.
mass times gravity if you're leaving gravity in, times 25. 0.25 since I'm in meters, or 25 if you stayed in centimeters. Right? And then we're going to balance that against the unknown mass, which is m times g times 0.05. Because it's not 0.05, 20. I don't know what I was doing. Sorry. Sorry about that. Yep. So that's why you don't need gravity. If you solve for m, you get that.